All right, hello and welcome to week 15, the final week of lecture here for Info 655, Digital Preservation Curation. This week we're looking at some issues that are on the cusp of affecting the work that we do, but are really a little bit more future facing, and we don't know what their full impact is going to be quite yet. It's one of the more interesting active areas to even just think and imagine how is it going to change our work in the future. So the goals are, we're going to talk about two big things. We're going to be talking about AI, and we're going to be developing an understanding of how that can augment our work. So my goal here is to say, artificial intelligence technologies are things that are going to be used in one respect or another. They're not going to replace the labor that we do, at least the way that we see them nowadays. They are going to be like a lot of other technologies, things that we use as a tool and eventually come to expect as just a natural thing that should be done like that. And we should know what those tools are, because all tools have good and bad uses. And we should also know how those tools got put together, because these are really complicated, culturally sensitive things that they have built. And it's not just, a perfect rational system. It has all the flaws of any other technological system. The second thing that we're going to be looking at is the blockchain and crypto and NFTs and things like that, which are a class of technology that's generally it's really confusing to cut through. What in the world is all of this stuff? How does it affect things? In my part of this work, I've heard all kinds of things from saying, NFTs make it not necessary to do collection management, to these things are scams that are never going to be useful for any purpose whatsoever, to what is the point of money when you have something like Bitcoin? So it is really hard to cut through all of that, and we're going to be trying to think about some of the ways that it could relate to digital preservation and curation. Now, for both of these things, what I'll be doing is explaining a little bit of how they come together. I don't expect you to leave with a deep knowledge of how these things work, but hopefully enough of an understanding that you can be skeptical about some of the more grandiose claims of what people say that any one of these technologies can pull off, or at least take a pause and figure out, will it actually be able to help you use it, or what are the flaws that you should be looking out for if you employ one of these tools. So this first half is going to be about artificial intelligence. Let me define a couple of things. When I say artificial intelligence, I mean that moving wall of things that we think machines can't do and only humans can do, until we figure out how to make a computer be able to do it. So, back 50 years ago, it might have seemed like science fiction to have a computer that could recognize different people's faces and, be able to notify somebody that, this person has come to your door, and now you can buy a $50 doorbell from Amazon or Google that is able to do that. Similarly, having a conversation with a computer seemed to be a very difficult task, and not to say that chatbot agents are fantastic conversation partners, but it is the kind of thing that you do interact with them to some extent, and it is possible to treat that as a natural language conversation. Not a perfect one, but it's getting better over time. And finally, something like driving a car, which seemed, a pipe dream 50 years ago, and nowadays it seems still kind of distant. It's not as close as one might have thought even 10 years ago, but it still seems on the realm of you can hail a robo-taxi in Arizona nowadays. So it's something, this wall of artificial intelligence is always kind of being pushed back as machines are taught to be able to do some of these things that we thought only humans could do. And I just said my next thing there, how do these machines how are they built to be able to perform these things? And that's through a technique often called machine learning. That's a strategy by which you build a piece of software or a model of some kind, and you slowly improve that thing, because if you set out to build something that could, we'll just say, drive a car, sure, you can teach it when you see a sign, speed up. When you see a sign that has a lower speed limit, slow down. You could do those things. But in order to handle all the edge cases that it takes to drive, to be able to say, okay, well, this is the speed limit, but I also see somebody crossing in front of me. Also, it's really dark, and so I can't tell if that person is really a person or not, or if it's just a plastic bag. You have to be able to build software that can be improved by the software itself, and to continue to be upgraded to handle these kind of edge cases and boundaries that you can't model directly yourself. So you have to have some sort of technique so that the software can be improved, and generally we can group those under a thing called machine learning. Now, when you do AI, when you do machine learning, the core steps that you're going to do are you're going to get a big data set, and that data set's going to have a bunch of input data and a bunch of results. And your system that you're building, your AI that you're building, you're hoping that when you give it that input data, it will be able to produce those results. And so you build your initial version of that AI, a piece of software, or a model, you might hear it called. And what you do is you run that data through that software, and that data then produces a set of results. That set of results will be wrong, but the key point is that you look at how wrong it is. You compare the results that you wanted to the results that it produced, and then you go back and you tweak a bunch of little things in the AI, and you repeat. And you do that thousands of times, millions of times, many, many times, until that AI finally produces something very close to the results that you want to see. And I keep using the word you here. It's not like a person is going through and doing all these tweaks. This is part of the machine learning thing, is that you've built an algorithm that can go and adjust all of the little pieces of your software so that it will be better the next time, the next run through. But as you go through training, you get to a point where you're like, this is doing really good on my test or on my training data set. So now I'm going to test my AI against some new data, some data that I've never run through this thing. I'm going to see the results that it produces. And if it does well on that, well, then I might actually start using that AI for the purpose that I had originally thought. So that's the general thing. You get training data, you train a model against that data, you then test that model to see if it's doing well enough, and then you go into production with it. And for an example of this, let's look at this example called the Modified National Institute of Standards and Technology Database, a set of 60,000 images of handwritten numbers, and a corresponding set of 60,000 numbers that each of those images are supposed to represent. So this data set consists both of those images and those labels for that images, or for those images. And all of these images are normalized so that they are just purely black and white images. There's only white pixels and black pixels in here. So back in the early 80s, a strategy that you would have had to take this data and to produce the numbers that these images have would be something called a neural net. And what is a neural net? Well, it is a way that you take a bunch of information and you do some of the basic math things that a computer is good at. You do a bunch of addition and a bunch of multiplication. You add together all these little pieces of data in many different combinations, and you do that a couple of times. So you take a bunch of pieces of inputs, you combine them in a bunch of different ways to get a new set of numbers. You combine those together in a bunch of ways to get a new set of numbers. You do that twice or 100 times, depending on the architecture that you want to run, and then hopefully you get the results that you want to do. Now, you apply a machine learning process to that by saying, well, once I ran that data through and I got the results out of it, I'm going to go back. I'm going to tweak all those little multiplication and additions that I had inside of my system. So I'm going to apply a mathematical process to tweak all of those things, and then I'm going to run it through again. And I'm just going to keep doing this over and over again until the math works out and the pattern that I'm looking for is produced by all of these parallel calculations. So in this case, Here's a example of a neural net that you would see to applied to a problem like the MNIST data set. So to explain what this diagram is, you have 3 columns of circles. The first column here, you'll see is labeled input layer, 784 neurons. They call it neurons because they are trying to get this analogy of maybe this is how a brain works. In some ways, that's an accurate analogy, but it's misleading in that, that circle is just a input where you put a number. It is a diagram of one of the 784 number inputs for the start of the calculation that this net will do. Now, there are 784 inputs because each input is going to be the color value of 1 pixel in that image. The first input would be the color value in the top left corner. The last input will be the color value probably in the bottom right corner. And so a 28 by 28 pixel image has 784 pixels. That's why you have 784 inputs. Now you see that first column of circles. Each one has a whole bunch of lines emanating from it. In this case, 15 different lines. And what that is representing is to say the first action that this net does is it takes each input and it multiplies it by 15 random numbers and sends it over to one of those circles in the middle column. And it does that for each of the inputs. So you have 784 numbers multiplied each by 15 random numbers. And it's 15 random numbers each time. Like none of these numbers are purposely chosen. So that's well over 10,000 calculations. And as each of these numbers arrive to that middle layer, you add them together. So each of those 15 circles in the middle is the sum of 784 multiplication operations. So you have 15 numbers in the middle now, and you're going to do the same thing again. You're going to take those 15 numbers. Each of them is going to be multiplied by 10 random numbers, and the results are going to be sent over to the 10 circles over on the right. Those 10 circles correspond each to one of the labels that you want to achieve. So we have these labels here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And each of those labels is the result of the addition of the 15 different multiplication problems that you just ran, each one from something in the middle there. So the way that we run this is that we take that image, we get all the color values, we load them into our first layer of our net. We then pick a bunch of random weights and we do all of our multiplications, and we fill in all of the 15 values in the middle layer of our net. We do a bunch of multiplication with our random values and put them over to our last level. And then we pick the number that is the highest at the end. So we have these 10 different circles, and I'm going to say, for instance, maybe the highest number in the end was that third circle next to number 2. So this neural net would say that picture that I have right there, that dark line in the middle of a white square, this neural net by default might think that it's a 1. Might think that it's a 2. That would be wrong, but all neural nets are typically wrong on the first try. The goal is that you then take that, you have a piece of math that allows you to adjust all of those random numbers for the multiplication that you did, 10,000 of them, and adjust them all a tiny little bit in the direction of of the right number that you want to be able to receive. So there's some math that tells you exactly how to do that, but you have a computer do this for you, and you do that over and over again. After thousands or millions of times, you'll have a thing that will take any 28 by 28 pixel of a pixel image of a number and be able to tell you what that number is with 90% accuracy. So that's pretty cool. That is pretty cool, but why it's not really good enough. The MNIST thing was built because what people really wanted was a system by which you could feed a check like a personal check into like an ATM and have a machine read it and be like, oh yeah, I can tell this is a check for $900. Great, credit it automatically and automate that kind of thing instead of having a person have to read every single check. So this was in part a way to help automate some of the most tedious clerical parts of the financial system. 90% is cool technically, but that's still a lot of room for errors. There's still a lot of bad checks that are bouncing around the system. So this doesn't really completely replace humans. It just adds maybe a first pass auditing tool onto how much is on a check. Now, modern neural nets, that was early 80s technologies, modern kind of AI approaches to this add in some additional technologies. So this is a diagram of what's called a convolutional neural net. This thing can reach 99.9% accuracy. When you look over on the right side of the diagram, you'll see something that looks very similar to the neural net that I was just on the last slide. But the change here is that instead of just treating every pixel as a input value and just multiplying those and adding them together and somehow hoping that that's going to give you the right answer, you are first applying image filters to that image. So you're doing things like applying sharpening filters or blur filters or things like that. So those are called convolutions in this case. And you apply a bunch of random combinations of these things. And then at the end of the day, you get a set of 64 different 7x7 images generated by your very first input image of 28 by 28 pixels. And so you take all 64 of those images and use those as the input for your final layer or your final couple layers of the neural net to figure out what that thing is. Okay, so a little bit of difference in the technology, but generally we're doing the same thing. It's a whole bunch of math, and then you see how wrong it is, and you go back and you try to improve it over time. So let's see a demo of one of these things work because they're pretty cool. So for instance, that's a 1. Amazing. That's a 2. Very cool. That's a 3. That's a 4. What if I draw my 4s like that? Still understands them. This does a pretty good job. And you can see it even gives me a confidence score and gave me 100% confidence for all of those things. Now, it is important that you realize there are limitations in this approach. So we see over here, this thing will only recognize 0 through 9. It is trained to be able to label something as one of those 10 things. So that means there are some problems here. There is some bias built into the system. For instance, this thing doesn't recognize Chinese numerals. Let me give it a 1. Nope. Thinks it's a 2. Let me give it a 2. Thinks it's a 5, but really not that confident, so it gives me a question mark. Give me a 3. This one still doesn't really get it. So only recognizes Latin Arabic numerals, doesn't do Chinese numerals. It's also only as good as its initial training set. So if you have trained this thing on a bunch of Americans writing Latin numbers, you might not get other versions of those numbers. For instance, some Germans like to write their 1s as this, and you'll see here 50% confidence that it's a 1. Not that sure if it is or not. And you can say, yeah, this thing was not trained on numerals produced by German handwriters, which, not surprising, it's an American data set. Another thing, it does not know if the output's useful or not. I can give it something like a 3, and it's like, yeah, that's great. What if I give it a 13? It still thinks it's a 3 because the AI has been trained to treat this entire thing as a single numeral. So these things will always have bias, and looking at numbers, I don't know, maybe not the most exciting kind of bias, not the most meaningful kind of bias, but they start leaking into all kinds of other places when you start looking at other applications of AIs. So for instance, speech recognition, which is a very AI-driven thing, has a lot of these problems. For instance, A English speech recognition does not understand German. A English speech engine, if it only was trained on American English, may not understand British English. And a English speech engine will not be able to know that, a bilingual speaker is actually changing between languages. And for that, I'll show this little clip here of a small child within being interviewed by somebody. And this is a linguistic thing to just show kids switching between languages, but the subtitles here are auto-generated by YouTube, and they are wrong. So there's some correct things there in Spanish, but then it sounds, these captions are correct. And yeah, it just completely loses the thread eventually. That's not what that girl was saying, but it's entirely because it could understand the English, but as soon as Spanish came in, only some Spanish words that were in its lexicon were recognized, and the other ones were jammed into something that was more American English. So these things have problems, and it's everything is a different kind of design constraint. It's very hard to make a general artificial intelligence that can handle all of these situations. So that is annoying. And now let's get into bad. There are biases that get encoded into these things. So it's important to recognize that. And when I was pointing out those examples of your training set determining what your AI is good at, well, if there's one thing about saying, hey, this training set or this thing is only trained to be able to recognize certain kinds of data, but what if there are patterns in your training set that you don't realize that you have and your AI is being trained to recognize? So things like, the fact that racism is just a thing in America and the rest of the world, and many of our data sets are incredibly racist because the traces of racism are in all the data that we produce. And as a result, when you look at the training data sets that people use, especially because they're so often used for commercial priorities, you will see that they reflect the reinforcing racism of the way that society is structured in America. If your particular identity is more marginalized, and that is some aspect of that is evidenced in something that somebody is training an AI on, well, your data is going to be marginalized in that training data set as well, and you're less likely to be well represented in that AI testing. So you will be less well recognized there. And especially, we can start talking about really kind of garbage situations. Garbage in, garbage out is a computer science term for if you give something bad data, you're going to get bad results out of it. So for instance, here's a one set where the various tech companies, when they initially launched face unlock algorithms, their face unlock algorithms were trained on large corpuses of light-skinned people, typically white or East Asian people. And as a result, a lot of people with darker skin found themselves not being recognized by a phone. A phone that was just widely promoted to be really good at recognizing humans, and it's saying, well, I can't recognize you. That's a hell of a message for your phone to be telling you right there. So here's an article where realizing this, what Google did was they said, well, we need a bunch of people or pictures of people with dark skin. And they went to a contractor. Contractor said, yeah, we'll do that for you. And then started going around and asking homeless people for permission to take their pictures because they were having a hard time getting permission from other people. So one ethical problem compounding on top of another ethical problem there, all in the pursuit of fixing a bias in a training data set. Here's another one, AI developed by Amazon for screening resumes. Amazon's like, we're a huge company, over 100,000 people work here. We get millions of applications a year. Could we use an AI to figure out which of these applications are the best applications so that we don't have to go read through all these applications? Well, what's a training data set? The people that already work at Amazon, they apply to work here, so therefore their resumes are probably the resumes that we want to see future applicants submit. And surprise, surprise, well, the hiring decisions at Amazon were reflected all kinds of biases. And so it's not like you could say Amazon was a diverse workplace. And as a result, their AI was able to correctly identify people that went to elite colleges, were typically white or East Asian, were typically male. Yes, they looked like the current Amazon tech workforce, and so that's what their AI was able to pick out of a resume. Garbage in, garbage out. Finally, there's this really fantastic example from YouTube where the part of their training data set that was biased was to say that they were trying to figure out how do we recommend videos to people so that they continue watching, because the longer they watch, the more ads we show them, the more money we make. And so for their training data set, they had a bunch of videos. And for their training outcomes, they said, well, which one of these videos get the largest amount of engagement, the longest time watched? Well, it turns out when you show extremist content to people, they tend to keep watching, whether it's out of interest or outrage or whatever. That kinds of divisive content is the stuff that keeps eyeballs glued to the screen. And so their AI said, you know what you should do? You should be continuing to pound all kinds of conspiracy theories and other things at people, because that's what's going to keep them watching. And that's what their AI recommended to people. So this is an article talking about the extremist content that got promoted on YouTube because an AI said that it kept people engaged the most. So there is bias there, and that is a good reason to be skeptical of AIs and something to be careful about when somebody promises magic out of one of these things. Now, another thing that I want to point out about AIs is that so far we've been using them to classify data, to say, like, I have a thing, can you tell me what kind of thing it is? Is it this kind of number? Is it this kind of word? That kind of thing. But you can also use AIs to generate data. As I said, this is math. You're going from big complicated data to just a single label. But like all math, you can go backwards. You can maybe take a label and apply a bunch of random calculations to it, and you can get something more complex. And so this diagram here is a generative convolutional neural net. It looks very similar to the one that we saw a few slides ago, except the smallest part is on the left and the biggest part is on the right. So instead of having the input be a big picture, what you have here is the input's a small number and the output is a big picture. And that allows you to do some wacky things. So what if you take one of these generating AIs and one of these classifying AIs and run them against each other? So you have one AI creating data and another AI classifying that data. And you train that AI to say, like, can I tell if this thing that this other AI is generating is a real picture or not? Well, then what you get is you have a generator that's trained eventually to invent really realistic pictures as they continue to do a better and better job of recognizing these patterns. And famously, Adobe created this example. This person does not exist. And as you reload this page, each of these images are entirely constructed by an AI. These are not people. These are just pixels put together by a bunch of algorithms that really look like people's faces, but these people do not exist. They also do have a one for cats and chemicals and horses and a few other things. So If it's scary to look at people's, here's some fake cats. That's always a little bit nicer. All right, so that is one thing. This is also where things like deep fakes and other kinds of uses of AIs come from, is you are improving a generating AI to do a better job of mimicking how a human would produce data. And there's still some questions about is there any complicity, because, libraries, archives, and museums were really big sets of training data for somebody that wants to work on this kind of stuff, whether it's classifying or generating and things like that. And it's one of the places that I think is maybe a place for abuse, and somewhere where we have to be careful about what kind of access we promote to our collections. But let's talk about some good uses. That was a lot of scary stuff. Let's talk about some good stuff, some things that you could do. So AIs, because of the work that we do, a lot of it is classification work, and we've talked about some classification stuff that AIs can do. So let's dig into those kinds of things. Like, can they be used for appraisal? What kind of file format is this document in? Can they talk about like the language that was written in? We could use it for description. Like, hey, I have this really big, long audio file. Can you tell me if it's music? Is it spoken word? Can you recognize how many people are speaking in it? Can you maybe recognize the person? Hey, can I have a system that can do a better job giving me related material that I might be interested in? Maybe not extremist material, but, can I build a better recommendation engine to find stuff? So let's look at some examples here. One of them is this example. This is a text format classification AI. And what this does, this is a Jupyter Notebook, so it demonstrates the code that is being used. This was built by a tech lead over at the United Kingdom Web Archive. And what they wanted to do was to build something that is able to recognize what kind of text file something is, because it's hard to tell what a text file is. It's just text. You don't know if it's HTML or actual text or a Python script or a CSS file or a data file like a CSV. And they trained a small classifying engine to do that. And here you can see in the results matrix that this classifying engine did a pretty good job. All of these are true positives, that this is a file, we'll say for this column right here, this is a Java file, and 50 of those Java files were predicted to be a Java file. 2 of them were predicted to be a C++, and 1 of them was predicted to be a C file. So that's pretty good accuracy. This is purely experiment to see how this kind of a thing could work, but this is one of the places that you could use this. You could also use this to try and figure out like what human language something was written in, like German or French or things like that. You train an AI to classify it, and now you can start tagging up images that you've taken of text because you can recognize the languages in them. Let's look at another one here, using AIs for appraisal and description. This is a project happening at the Indiana University called the Audiovisual Metadata Platform. And they're looking at a really kind of complicated set of stuff here. Here's a diagram of one of the ways that they're looking at this. What if we run a whole bunch of different services on a single file and start generating metadata that a cataloger could use to enhance a description? So for instance, we have an audio file. We figure out where's the silent part, where is the parts with noise. Once we have noise, we figure out if it's speech or music. If it's speech, let's figure out the language. Let's figure out who the speakers are. Let's try to create text from that speech. And then maybe we'll even go farther, because now that we have text, we can start saying, well, are there names there that we recognize? And are there places that we recognize? And can we start matching those names and places to GPS coordinates and authorized names? But what if we have music? Well, if we have music, let's see if we can detect if that's commercial music, because then we have a rights question that we need to answer. And if it's not commercial, maybe we can start generating information about the musical qualities, like the beats per minute or the genre or the instruments that are played. And all of these are different AI services that they can use the APIs for to send data there and get a result back and be able to present that to somebody to be able to build a description. So this is a pretty cool thing. It's ongoing. There is another round happening. It's going to, I think there's a project report that I've linked to, but they're continuing to work on this system. Another thing that I want to point out for discovery and access is this cool GitHub repository built by the Carnegie Mellon Museum, the Carnegie Mellon University Archives, I believe. And what it is doing is they are just trying out some various AI techniques on various things. Like, hey, can we take a bunch of subject headers that have been added over time, and can we extract various entities of them to have a more standard set of subject headers? And as you read through this report, you'll see, they do a pretty good job, and they kind of simplify and standardize what they're able to do here. Again, this is experimenting, but looking at another way that we could use AI to perform quality control on cataloging or to otherwise enhance human-derived work. Finally, there is this example of Discovery, which is built by Andromeda Yelton at MIT, which is a recommendation engine that is able to find theses by, you look at one thesis and it will show you another one. I'm going to look for a rocket. And sure, this one right here. I search for it. And what it's doing is it's actually parsing the text in all of these theses, and it's building a model of what that thesis is about, and then recommending theses that might be more similar to it based on the topic modeling inside of there. So here we see a preliminary design of a liquid bipropellant microfabricated rocket engine written in 1998. And you'll see that there are other theses from very different departments that this is recommending as potentially something of value and of interest if you find that one thesis interesting. So another cool use, a recommendation engine built on an AI. So that's a cool thing. And again, I'm unfortunately, most of these things are cool things because we're still not entirely comfortable with the idea of just turning over this kind of work to a computer. We're still not entirely certain about these results, especially for fields like ours where we like certainty, we like being an authority. It is a scary thing to say, well, we have 90% accurate confidence that this thing is a good idea. So we're probably going to continue seeing more experiments in this field, but in general, it is a nice thing to keep track of because I think we're going to start seeing these tools being used as things that we're actually using. And that is a good thing in some senses, but it is a bad thing because as some of those bias examples that I showed demonstrate, these tools do still have problems, and we should be able to ask very measured questions and say, is this actually achieving some of the other goals that we want to achieve within our institutions, like reparative description and things like that, or is it furthering the harms that we have caused in the past? So hopefully that gives you a better idea of what's going on with this AI stuff.